Hello everyone, this is the solution video to Quiz1. Now, the problem was to code a function called dom_data, which gets basically the dominance factor and some data about it. We have a symbolic polynomial here, PCS, which is defined, for example, like this. We are going to call the function here, and it will return us the dominant poles zeta and omega n, the dominance factor, and if the polynomial is stable or not, basically. So let's dive right into it. I've created and prepared a main function here, sims s, and then the polynomial, and then the function call, and then we have our function, which accepts basically the polynomial in this case. So now let's first of all start by defining our symbolic variable s. Now, since we have PCS, we can basically calculate the roots of it. So C poles, or the poles, we can use coefs, or we can use the solve method here. PCS equals 0 should give us basically C poles here. Now, if we call the main function, we'll basically get an error because we didn't assign anything. So that's the assignment problem here, because we promised to assign m, zeta, omega, and stable, but we didn't, so we get this error. But I can see that we have certain roots here. So therefore, we have basically calculated them, converted them to double. Now, what we can basically do is we can check for the real part of the poles. So let's take real of the poles. Let me run again. There we go. Now we have the real parts of our poles. A quick check would be the following. We could eliminate the ones that are actually positive. So this. There we go. As you can see, none of them satisfy this. So if we get basically C poles, this here, temp, we can see that we get an empty vector here, or an empty structure here. And if this is empty, then it means that it is stable. Because what I'm doing is I'm kind of checking for positive real values of roots. If they are positive, it means that they will be on the right half plane, therefore not stable. So therefore, I check for the positive ones, and if they're positive, I'm going to basically conclude the stability. We can see here that it could be done differently by checking if they're negative and if the vector has the same length as the number of poles. But this seems to be a better way, in my opinion, because it checks for emptiness. If it's empty, it's by definition a stable polynomial because all the poles are on the left. So this can directly be assigned to stable is empty. And this can also be used if stable, like this, because then the dominance factor does not really make sense. If it's not, what we can do is we can just say m is not a number, like zeta is not a number, omega n is not a number, so we can see that it's not stable at all. So let me call it again. We should have stable, but of course, since we didn't assign everything, so let me just quickly fix that maybe. M is equal to 0, zeta is equal to 0, omega n is equal to 0. Let's see what the result is going to be. Now we can see we have basically the outputs, it is stable, and we've assigned to 0, not to none. So yeah. Now, so we have basically implemented the stable portion here. So what about the other ones? What we need to do is basically, first of all, look for actually imaginary pole pairs, because by definition, if we have zeta and omega n, it means that we will have a complex conjugate pair. So for that, we need to eliminate the ones that don't have imaginary parts. So from the poles, I get the imaginary parts. If they are not equal to 0, I'm interested in them, because these are probably the complex conjugate ones. So let me show you them. Let me, by the way, add a semicolon to suppress that. There we go. These are the complex conjugates ones. Whereas the actual vector had more poles in it, I have basically eliminated this pole here, and I'm interested in the complex conjugate ones. So, so the possible dominant poles are going to be stored in here. Yeah. Now, if these are probably the dominant poles, then the residue poles are probably the inverse of these. So, like this. Actually, they should be like that. If we have a real pole, if zeta is greater than 1, then that's not the dominant poles. Here we are talking about, of course, dominant pole placement. Therefore, if something is near the origin, it is going to be dominant. But what we try to do here, because of zeta and omega n, you should pick that up, we're looking for specific systems where zeta and omega n are present and are the dominant poles, or pole pairs. So we kind of separated the dominant ones into the non-dominant ones. If we wish, we can just put in a negative sign in order to get rid of the negative sign. Now, from the dominant poles, I'm interested in the minimum real value here. So let me take the real value here, because you can see we have two of them. So this would be 0.5 plus minus that, and 0.1 plus minus that. So I'm kind of interested in 0.1 because that's the dominant one. So this is going to be the index. And actually I want to know yeah, we have the real parts of the dominant poles. I'm looking for the minimum one of these. And the index where the real parts of the dominant poles are not equal to just this minimum are going to be added to the residue poles here. Res poles. The real part of dom poles index. If we didn't mess up stuff. And the dominant pole is going to be dom poles the index here. So let me show you what I mean by that. So I'm looking for the index where the real part of the dom poles, basically these two pole pairs here, I'm looking for the ones which are not the minimum. So I'm looking for 0.5 plus minus that. This index is going to be holding that information. Since I'm interested in these, I'm just picking them and adding them to the residue poles. And for the dominant pole, I'm just taking the inverse, basically, which is the minimum here. So I'm separating the complex pole pairs. I'm taking the minimum one. I'm adding the other one to basically the residue poles here. Of course, actually calling this residue poles is not really accurate at this point because, well, these are the real values of the residue poles because I'm adding the real value here. So let me show you what the index was and the C poles, basically the dom poles are here. It's index here. Oh, I misspelled it here. There we go. Now you can see I'm basically referring to 0.5 because that's not minimum, but this is minimum. So if I take the inverse, this will be 0, 0, 1, 1. If not, it is 1, 1, 0, 0. So I'm separating this. I'm taking the dominant pole here. So let me show you that one too. So what is res poles and what is dominant pole now after this separation here? Now you can see I have basically added the 0.5 real parts of the complex conjugate pair to the residue poles. Now, of course, this is not a residue pole. This is the real part of the residue poles, but I'm only interested in the real parts because I'm going to calculate M in a moment. So there we go. And the dominant pole in itself has basically the dominant pole pair. Now, I am kind of ready to calculate what the omega n and zeta values are. So let's begin with sigma, which is basically the real part of the dominant pole. I can just choose one of the dominant poles here because it's a pole pair. And I would then get omega d, which is going to be the imaginary part of the dominant pole. Now, I could also take the absolute value to be a bit more safe. If it's the negative one, I'm just getting rid of the minus sign here. Now, if I'm interested in omega n, let's actually calculate zeta here. So zeta is basically going to be calculated with the a tan d omega d divided by sigma here. So omega d is the imaginary part, sigma is the real part. If you take the tangent, you will get the angle here, the inverse tangent. And if you look for the cosine d, I'm sorry, it should give you basically zeta here. And we also know that the natural frequency is basically sigma squared. So sigma squared plus omega d squared and the square root of that. If you're not familiar with sigma omega d zeta omega n, just write down s squared plus 2 times zeta times omega n times s plus omega n squared. solve the roots, which are basically minus zeta times omega n plus minus j times square root of 1 minus zeta squared times omega n. If you solve this polynomial, you'll get the solution here. And then you can work your way out. I have basically defined this as sigma here. And this is basically omega d. You can see if you take sigma square omega d squared square root, it will give you omega n. The stuff will cancel each other out. If you look for the tangent here, you will get square root this divided by zeta here, and then the angle. And if you use the Pythagorean theorem, the triangular calculation, you will see basically that this will be zeta, so it's the cosine. Zeta omega n divided by omega n will give you the cosine. Yeah. Now, we have actually calculated the dominant pole, extracted the zeta omega n. The only thing that is left is m at this point. Now, let me run it again. What is zeta? What is omega n? And what is stable looking like? So, and what about m? Now, if you remember, we have this rest poles here, which we have constructed carefully to separate the non-dominant parts here. As you can see. And we know what zeta times omega n is, which is the real part, or sigma is, basically. So what we can do is we can basically look for the minimum here. The minimum of rest poles, which is going to be the closest to the origin, divided by sigma should give us m. So let me actually get rid of the semicolon here in order to see. There we go. M is 5. Now, I knew that this one is the dominant one. And you can see that there's a 5 times ratio here. 5 times 0.2 gives us 1. And that's basically the closest one here. S plus 4 is far away. This is a stable one because we can see this is stable, this is stable, this is stable. And we can see that this is 2 times zeta omega n, so divided by 2. Omega n is 1, zeta is 0.1. We extracted all the information that was necessary. So let me recap. We defined symbolic s, we solved the polynomial roots, then we have looked for positive or equal to 0 real parts. If that's the case, then it's not going to be stable. If any one of the poles satisfies this condition, then this is not going to be empty. If it's empty, all the poles, real parts, are negative. Therefore, the system is stable. If it is stable, we have looked at non-zero imaginary parts. And then we have basically separated the poles in terms of imaginary parts. The ones that have imaginary parts will be by definition probably the dominant poles. They are the candidates. And if they are real poles, they are probably the residue poles. For now, at least. Then we have looked for the minimum real part in the dominant ones. Now, these are complex roots. These are real roots, so we're kind of separating them. And we're looking for the minimum real part complex root here. And the other ones are basically pushed to the real poles. Their real part is pushed there, because I'm not really looking for the poles itself. I'm just looking for the real value of them. The dominant pole then remains to be the minimum real part complex conjugate pair. We've separated them. Now we have the dominant pole. We can work our way out to calculate sigma and omega d. Based on sigma and omega d, we can get zeta and omega n. Now the remaining real parts are stored in rest poles. Now dividing them to sigma and taking the minimum, or taking the minimum and dividing them to sigma, gives us basically the dominance factor, and we are returning this stuff here. So hope that this was helpful. See you in the next videos.